Thank you very much for the introduction. Hi, I'm Miles, and today I'm going to introduce our MobiSys work, Vronicle. This is a joint work with my colleague Yoshi, Arjun, Jing, and our collaborator from Microsoft, Sharat. Video has become extremely popular in modern society, especially on social and entertainment platforms. And it doesn't stop there. Video is also used in a lot of important use cases, such as news, identity verification, video conferencing, and even evidence in the court. And we know that a lot of video have gone through some video editing, like using blur filter for privacy protection, and maybe using denoise filter for better view of the video. But not all videos are processed truthfully. There are a lot of manipulated and fabricated videos. And I think we have now known about the words fake news, fake videos in the past few years. And this is actually causing problems. For example, the US House Speaker, Nancy Pelosi, her videos have been found edited maliciously to make her appear oddly. And these videos were spread across social media platforms. There's also a new kind of technology that is arising, which is deepfake. Using just a few images of the target actor and the source actor, a completely fabricated video can be easily made. And there are some existing detection-based approaches that are trying to fight against such fake videos, including just using human eyes and ears, and also using some smart detection algorithms. But we think that with the fast advance of technologies such as deepfake, it becomes extremely hard for these detection-based approaches to keep catching up. So that's why we would like to advocate for our prevention-based approach, which is by using provenance information. And it helps the consumer of the video to authenticate the video. More specifically, we want to provide fine-grained provenance information for the video. And it can help the consumer to authenticate both the source camera and all filters that have been applied to the video. Let's get into the design. First, let's take a look into a normal flow of the video. The video is first captured using a camera device, where there could be a lot of frames in this video. These frames are then sent to the video post-processor, which can run on either the camera device itself, such as a smartphone, or be offloaded to a dedicated and powerful server. After these frames are processed, they will be sent to the video consumer. Now let's see what if there's an attacker. The attacker does not need to be a third party. The attacker can also be the camera device owner or the video post-processor's administrator themselves. They can target at the video after it is captured because it is stored as a file, or after the video is processed because it is also stored as a file at this moment. And that's why we would like to introduce our provenance-based flow of the video. First, along with the video, there is the provenance information generated. The provenance information does not only contain information about the video, but also information about the camera device, where it can authenticate the source camera. And then along with the video, the provenance information is also sent to the video post-processor. When the frames are being processed, the provenance information will also be updated. And basically, it's just each of the filter that is applied to the frames will also leave some historical records to the provenance information. And this helps us to authenticate all applied filters. And after all of this, both of the provenance information and the updated video will be sent to the video consumer, where the video consumer can look into the provenance information to gain high confidence that the video is authentic. But there are more possible attacks. Let's say what if the attackers have control of the camera device or the post-processor. In this way, they can directly just generate or modify the video or the provenance information directly. That's why we make use of trusted execution environment. Trusted execution environment is essentially an isolated environment. Examples including ARM Trust Zone, Intel SGX, AMD ICV, and so on. Below is a figure of an illustration of the ARM Trust Zone. On top of the hardware, you can see there's a wall between the normal world and the secure world. Where in the normal world, we have the normal OS, such as Android, iOS, and so on are running at. And in the secure world, we have the trusted execution environment. And in Vronicle, we aim to move all the codes that process both the video and the provenance information into the TE application. So now we have known that we use provenance information to authenticate the video. And then how do we authenticate the provenance information itself? That's when we make use of a feature of the TEE. It's remote attestation. Remote attestation basically involves two parties, the verifier and the prover. The verifier is actually trying to verify the state of the prover. And in Vronicle, we use this to identify the exact codes that is running inside of the TEE. And now let's take a look into our complete threat model. First, the camera device vendor is treated as part of our TCB. Second, the TEE vendor, and the remote attestation servers, they're also part of our part of our TCB. And for the possible attacks that we want to protect against, we majorly consider two types. The first type are targeting on the video or the provenance information directly, where the second type of attacks are targeting on either the camera device or the post processor. And we consider any kinds of TE-related attacks as out of scope, and we also do not consider availability and confidentiality-related attacks. Now let's take a look into our design of the post processor. The very first design that came into our mind is this all-in-one design, where we have the decoder, all the necessary filters, and the encoder in a single TEE unit. However, we soon realized that there is a problem in this design, which is verification. With remote attestation, we are only able to verify the codes that are loaded at boot time. And with the amount of possible filters, we also need to get all of the code signatures of the different combinations of these filters, which are enormous. And to solve this problem, we propose to we make use of fixed function post-processing unit, where each of the TE unit only has a single function. It can only do like applying a filter, do the decoding, or do encoding. And then we make use of multiple TE units for processing a single video. And with this design, we significantly reduce the number of code signatures that we need to recognize. Therefore, we make verification of these TE units practically possible. And now let's take a look into a concrete example. First, the camera device captures a video, and the video is then sent to the scheduler inside of our post processor. And in this example, we can see that there's a decoder TE unit, there is the denoise filter, and there's also blur filter and the encoder TE unit. The video is first dispatched to the decoder TE units, where the video gets decoded into raw frames, and each of the raw frame has its own provenance information. Then each of the frame is sent to the denoise filter first, along with provenance information updated, and then they are sent to the blur filter, and then to the encoder TE units, where all the raw frames, the processed raw frames, are encoded together, and all of their provenance information are merged into a single updated final provenance information. And then along with the updated video, the updated provenance information is also sent to the video consumer. One thing to keep in mind is that only the blue boxes here, so the TE units, are trusted, where all connections between them and also the scheduler, they are not trusted. So please refer to our paper for more details, such as how do we keep updating of the provenance information for each of the raw frame, and also we have a detailed security analysis in our paper. For our prototype implementation, on the camera side, we have implemented a trust zone-backed safety net camera application. We haven't implemented a full TE-backed camera, but we have noticed that there is industrial effort on that, such as the TruePic TE camera. And on the post-processor side, we have implemented a prototype on both trust zone and also the Intel SGX. And we have treated our TE unit as a trusted application in the ARM trust zone, and we treat it as an enclave in the Intel SGX prototype. On the consumer side, we have implemented a verification program along with a VLC player for video playback. And for the actual prototype, we implemented our camera side on a Samsung Galaxy S20 phone, and we implemented the trust zone prototype on a high-key development board, and we implemented the Intel SGX prototype on the Artery Confidential Computing VM, and we use a normal Ubuntu desktop for the verification program. We have integrated a total of 7 filters into our filter frameworks. They are the blur, sharpen, gray brightness, denoising, white balancing, frame erasing filters. We have also evaluated 2 different combinations of these filters. And on the x-axis of these 2 figures, you can see different filters, and on the y-axis, you can see the execution time. So on the figure of the left, which shows the trust zone prototype, we can observe that we achieve usable performance, where on the right figure, we can see that SGX-based prototype provides much better performance than the trust zone-based prototype. We have also evaluated both our prototypes on different resolutions and different number of frames. So one thing I want to clarify here is that by default, we make use of 720p resolution and 60 frames. On the 2 figures above, we can see the x-axis is representing different resolutions, where on the 2 figures below, x-axis is representing the different number of frames. And by observing these 4 figures, we can say that both of our prototypes achieve linear performance. To study how Vronicle can perform in real-world, non-real-time use cases, we have also done a comparison with YouTube. For this comparison, we make use of a 10-second 720p 30 frames per second video. And in Vronicle, we apply a total of 6 filters, and it takes an average of 44 seconds. Where on YouTube, it takes an average of 31 seconds, where from the start that we click the upload button to the point that we can actually see the video. And in this comparison, we can say that Vronicle has the same performance in the same order of magnitude as of YouTube. And therefore, we believe that Vronicle can provide practical use in real-world, non-real-time use cases. We have also done comparison with all of the related works that we have noticed, and only Vronicle can provide both fine-grained provenance information and achieve video-capable performance. In our vision, just like what the industry has seen, provenance is the most promising approach to defeat fake videos. And we are not alone in this path. There are companies such as TruePic, Serali, where they are focusing on the trusted, authenticated, and verifiable camera capture. And there's also the content authenticity initiatives by Adobe, where they have similar idea, but they make use of self-certification, where in our side, we make use of trusted execution environment and remote attestation. In conclusion, Vronicle uses verifiable provenance to prove the authenticity of the video. We have designed the fixed function TE post-processor to make the verification of each of the TE unit practically possible. We have a fully implemented prototype, and we have thoroughly validated it. Vronicle is fully open source. Please feel free to visit our website for more details. Thank you, and I can now take questions.